everyone. I hope you all enjoyed your lunch and that you had a chance to connect with other community members and visit with some of our exhibiting partners, and that you're fully prepared for the second half of the day that we have prepared for you. To kick things off, please welcome Daniel DB Doubrovkine and Prabhakar Sithanandam, principal engineers with OpenSearch, who are here to discuss what you need to know in order to scale OpenSearch to support hundreds of terabytes of data. They'll help you answer this question and present and explore some disruptive ideas for the next decade of OpenSearch. Please join me in welcoming to the stage DB and Prabhakar.
Thank you, thank you. Is everybody back from lunch? Do I need to tell a joke to have everyone wake up? Okay, I hear yes. So what does OpenSearch and elephants have in common?
I don't know. What do OpenSearch and elephants have in common?
Tons of memory.
That was a good one.
Thank you. I'm DB. I'm an engineer on OpenSearch. I've been working on this project for over a year. Amazon for about 3. I worked on helping launch AWS Data Exchange, a marketplace for data. Come from a long history of open source startup land, and I live in New York.
Yeah, myself, Prabhakar. I'm an engineer in OpenSearch. I've been with Amazon for close to 12 years and with OpenSearch for the last 5 years. I primarily work for the managed service part of the OpenSearch. I'm from Bangalore, India.
Thanks for making it all the way here. So in thinking about big data, I went to SlideShare and did a search for massively scaled Elasticsearch clusters, big Elasticsearch clusters, large data in Elasticsearch over the years, and I found a bunch of very interesting presentations and slides about the sizes of these clusters from going all the way back to 2012. So I found this really big guy out there. It had gigabytes of RAM, many cores, was indexing quite successfully 300 million documents at the time, which was about 299 million more documents than a search engine I worked on in the 90s that powered interesting websites. It had a terabyte index, including replicas, so that was quite impressive. Then I asked Prabha, like, what kind of deployments do we see in the managed Amazon OpenSearch service?
Yeah, I tried to look into what did the data look like a couple of years ago, and I found this use case on Pinterest. So Pinterest was having a 500 GB use case in their self-managed cluster, and they moved to OpenSearch back in 2020. And from it was 500 GB in their on-prem, and then when they moved to OpenSearch, it grown to 1.7 gigabytes. So it's like 1.7 terabytes. So it's 1 terabyte in 2012, and it became 1.7 terabytes in 2020. Yeah, maybe not that big. Let's see what it is today. So I tried to find what is the biggest cluster that we have in OpenSearch today, and found one of these biggest clusters. This is a 200 node cluster, and it has like close to 625 terabytes of data. This is used by a log aggregator service, and this cluster generates tens of thousands of alerts per second. Like it's huge, 200 nodes and like 625 terabytes of data.
Quite impressive. Do you have anything bigger?
Yeah, I can continue my exploration and try to find the other biggest clusters, and found another cluster which is also 200 nodes. Until then, I was thinking like the previous cluster was the biggest one, but like that was biggest based upon the data, but this one is biggest based upon the number of cores. This particular cluster contains 12,800 cores, and this is also used by a log aggregation service. And this is specially tuned for search use cases, pretty millisecond latencies.
That's a big cluster, 500 terabytes. But do you have anything bigger?
Yeah, I continued my exploration and found not a biggest cluster, but a use case. Like this particular use case is broken down into 35 different clusters, each of which is like 200 nodes. So like what we saw earlier was like the bigger in size per cluster and biggest in terms of processes. But this one is the biggest use case that is span across multiple different clusters. So all put together, this is the biggest use case that one of the biggest use cases that we support in OpenSearch today.
Interesting. So do I just go click a few buttons, deploy 35 times 200 node cluster, and then everything works great?
Well, it's not that easy. So maintaining clusters at this scale requires a real crafting, and then it requires a continuous monitoring. Because there's a bunch of bottlenecks that we need to deal with. Like talking about bottlenecks, I see cluster manager is the biggest bottleneck that we have with the clusters today. Like I can recall an incident that I happened to investigate a few months ago. This is due to the cluster manager. So this is a 200 node cluster, which is like operating happily so far, and there was a snapshot going on this cluster. Then, like one of the nodes went bad due to a hardware failure, and this trickled down a bunch of snapshot update tasks to the cluster manager. And for each of the snapshot update tasks, it triggered a cluster update. And for each of the cluster update, it again trickled down a bunch of snapshot update tasks. So this caused a spiral of events, and at a point in time, the cluster manager was not able to respond. It was like just stuck. Like we tried to investigate and try to do a bunch of things, but nothing worked out, and we finally ended up restarting the cluster. But that's not about it. When we restarted the cluster was not starting up. It's due to like the ping milliseconds, so we increased the time it takes to bootstrap, it connect to the other nodes, and then the cluster came up. So it required like effort from multiple engineers across multiple hours to get the cluster back up. So anything going wrong with the cluster manager is a real deal.
What other problems do these large clusters have?
Like other problem that I could think of is with the shard allocator. So shard allocator works great if all the shards are of equal sizes, but if the shards are of not equal size, like it doesn't do great. I recall an incident which I investigated a few weeks ago, wherein we had a cluster of 100 nodes, and data was like little different. So like it had few of the shards which are of sizes gigabytes, and a few of the shards which are in kilobytes. So what happened is in 100 node cluster, 50 nodes ended up with having all the bigger size shards, and 50 nodes ended up with all the smaller size shards. So when like this caused the latencies to go up, and when we investigated, we found these 50 nodes were getting all the traffic and they are super hot, whereas in the rest of the 50 nodes not getting any traffic, and like the resource utilization was like less than 10%. So to fix this issue, we manually moved the shards between the from the bigger nodes or the nodes with the bigger shards to the other nodes, and then yeah, the cluster was happy again.
So cluster manager, shard allocator, what else?
Other problem that we see is with admission control. So OpenSearch doesn't do great with the admission control, or I should say like it doesn't have any good admission control. So as we put on more requests, the OpenSearch cluster keeps on accepting the request, but it goes to a point that it doesn't respond any further. So like lack of admission control is one of the like biggest bottlenecks that we see with OpenSearch today. I recall an incident related to admission control. So wherein I got a like customer complaint saying that, oh, my cluster is like hasn't changed anything, but the query started taking more time. So I started investigating this cluster and realized that the traffic pattern is same now, but there was an increase few years ago. The latency started going up after the traffic was increased, but didn't go down after the traffic was down. So this was later, and when I investigated further, I realized that this is due to the fact that there are like a bunch of background tasks that started when there was an increase in traffic, which didn't complete it. So that caused the increase in the latency. So once the background tasks are complete, the latencies are back to normal.
I did see this too in my rotations where some tasks will get queued and the cluster seems to not be taking any traffic, but then it's still doing a bunch of work. And when you look at the work it's doing, it becomes quite unclear where that work came from or what it's up to. And then the JVM usage stays high. There was I remember a case where it turned out to be a bug in Lucene, and it was doing an infinite loop, and these tasks would just run for hours until killed. It took a very long time to get to the bottom of it. Turns out to be a bug, so it's not. There's nothing that the customer could have done in this case.
Right. Like we don't see storage as a bottleneck, but it does matter like when we want to retain the data for longer duration. So one like typical use case, this is more on the financial companies, like where they want to retain the data for multiple years for compliance reasons. OpenSearch does great when we want to store the data for smaller duration, but when it goes for when we want to retain it for years, like it doesn't do great. So like storage is a bottleneck.
If you look at these problems that these clusters are having, it gets progressively worse with all the other add-ons, plugins that can be installed on top of an OpenSearch cluster. So if a plugin today is Extends plugin, it's tightly coupled to the engine, and it can effectively do whatever it wants inside your cluster, and could easily take a cluster down as well. Do you have any examples where a plugin, useful plugin, did something really unexpected?
Yeah, I recall an incident with the analyzer plugin. So this analyzer plugin was added to the clusters, and then the memory shoot up immediately, like from like few, like it is almost 100% across different clusters. When we realized it was the analyzer plugin which is causing it, the thing is like though the analyzer plugin was not really getting used in the cluster, it was just being there. It caused an increase in memory.
So just because it's installed and it wasn't even used.
That's right. Yeah.
So what do people do? How do you deal with all these limitations, all these bottlenecks?
Yeah, like different customers solve for different use cases, and they do different things. So one of the like typical things the customer do is they do create two different clusters and ingest the data in both the clusters and use one as the like active copy. So like when the first cluster goes down, they switch to the second cluster. Customers also break the biggest cluster into multiple different clusters so that the failure rate is less.
Okay, that's horizontal scaling. And then can we improve the vertical side of this?
Yeah, like we can also use like other solutions with OpenSearch to make it work better. One such thing is like having a queue in front of OpenSearch, wherein like the data can be pushed to the queue, and there could be a client which reads from the queue and sends data to the OpenSearch. This helps in cases where we want to have like high ingestion. Like OpenSearch doesn't like scale for like that kind of request, so we need to have like something before that. And like customers also use like different storage solutions for long store retentions.
Makes sense, but in the end, I have these multiple dimensions of a problem. I want fast search, I want cheap storage, I want reasonable CPU utilization, and I have to deal with these with a number of shards versus sizes of the shard. It seems like a good, whenever you have a complex problem, the answer is always AI and ML. So have you tried maybe throwing all these different inputs into some ML model and coming up with like, this was what your cluster should look like?
ML might help if you look into one of the certain parameters, but not for the others. So an expert working on OpenSearch for like last 5 years not able to figure out like how to form a new cluster. It's that difficult. So, but we also like look into like a lot of small term items to improve the experience. Like some of the projects that we currently working on in search area is search back pressure. We talked about lack of admission control on the problem it causes, and with search back pressure, any search query which takes a lot of memory or a lot of resource consumption can be protected, can be killed, and that's a that way like we can have the cluster protected. We also have working on the asynchronous search. Previous to asynchronous search, if we want to run a long running query, we have to break down big single query into multiple small queries and run it. With asynchronous search, we can run the query, and the query actually runs in the background, and we can query the results as and when they are available. We are also working on the point-in-time search. Before point-in-time search exists, we have to take a snapshot of the index and restore it to a different index and start querying to get the point-in-time view. With point-in-time search, it comes for free. We are also working on other scaling projects with respect to the replication. Replication is the process of keeping the data in sync between the replicas, or we call as the copies. So currently in OpenSearch, the replication happens based upon the translog replication, as in like we ingest the data is ingested in the first primary node, and the data is copied to the second replica node, and then the segments are getting created. So as a number of replicas increase, this work is repeated across each node. With segment-based replication, the data is ingested just on the first node. The segments are created, and then the segments are copied to the next set of nodes, that saving on the latencies when we do I ingestion. We are also working on logical replication to the remote storage. So this data, like as and when the ingestion has happened, it also gets stored in a remote storage, and this can be used for like restoring and disaster recovery purposes. We are also working on cross-cluster replication. This is like replicating the data from one cluster to the other cluster. This is generally useful when the clusters are located in different geos, and the read-only replica can be used for faster latencies.
I think full cluster replication is cool. It replicates all the configuration and data, and then you can fail over when you need to, or maybe split traffic as well.
Yeah.
Very cool.
Yeah,
what about storage?
Yeah. Continuing on the like other scaling projects, we are also working on storage for warm and cold tier. So whenever the data gets like rarely used or like less frequently used, the data can be moved to a warm storage, or like when it is rarely used or not even used, it can be moved to a cold storage. We are also working on a bunch of improvements related to the shard allocator.
There's also a number of projects around extensibility. If you saw Nick's talk earlier, it's pretty easy to write a plugin. You just take a direct dependency on OpenSearch core, and it extends the plugin interface. Then you implement a page-long worth of methods, and voila, you have a plugin that can easily bring your OpenSearch down, or can do something useful. We are introducing something new. It's an SDK that will sit in the middle between OpenSearch core and its extensions. Instead of coding against OpenSearch core, you'll be able to code against the stable SDK. The one amazing thing about the SDK is that it will instantly give you compatibility with many versions of OpenSearch. So you can, we already follow Semver on all server-side APIs, RESTful APIs, and otherwise. And you saw the difficulty of having to annotate all core methods as internal, not internal, public, not public. With the SDK, everything is public and everything is an interface. And it will follow Semver. So you can build a extension against the OpenSearch SDK, and it will work against OpenSearch, say 2.1 to 2 to 3 to 4, etc. With some hopes for compatibility across major versions as well. If you look at OpenSearch clients today, those are already compatible with OpenSearch 1x and 2x. The same client works against multiple versions. Our ideas around extensibility can be best summarized as the ecosystem of Visual Studio Code, where you have thousands of extensions, and the security of the Apple App Store, where things are well locked down, the interfaces are clear, identity, authorization, authentication are all going throughout the entire engine.
Yeah, plugins across different versions. That's super cool.
There are other ideas. I was talking to a few people in the room over the last couple of today and yesterday, and much of the projects in the issues that we've shown you are all about fixing existing bottlenecks, existing problems. When the engine runs out of memory, we'd like to cap that. When you run out of some other resource, we'd like to fail early. But maybe we can never execute a query if we think that it will overwhelm the server. Most databases have query planning, so if you look at a query, you can estimate how much effort it will be, and then direct it to the node that's the least busy, or maybe divide even the query in multiple on multiple nodes, or wait, queue, and so on and so forth. Now, this is a very hard problem because users run arbitrary queries, including queries on that are supported by plugins or extensions. So while it's not easy, we are hoping to introduce some query planning, and then costing, and then also create a feedback loop where the execution can compare its execution to the query plan that was created and see how it's performing, log and give all that information. Networking, one of the biggest issues in networking is a garbage collection. The GC interrupts whenever it feels like. and that causes blips on the network, and that causes lots of cascading failures. There are reactor pattern implementations that prevent GC, and we can maybe swap the transport mechanism that OpenSearch has by something that is not going to have as much garbage collection impact, which is really critical for networking. We already shipped a way to tag nodes, so you can create a dynamic node type for machine learning, and then you can run certain jobs, so you can target certain tasks on nodes that have a GPU. So we can start taking advantage of heterogeneous OpenSearch clusters. Today, everything has to be the same to be reasonably scaling a cluster, but it doesn't have to be in the long run, and you can provide dedicated nodes. We've heard some stories about Graviton improving 30% throughput, but imagine if you could divide your cluster in different types of hardware for specific purposes of search, indexing, etc. Maybe there are much larger gains to be had. OpenSearch is a distributed Lucene, but it doesn't have to be forever. There are other implementations out there that are similar or compatible with Lucene that are written maybe in C++ or Rust is the next big thing. So we are open to swapping Lucene out of this engine at least and experimenting with it. I think that could be a good idea. And speaking of native code, there is a compression at encryption at rest is easily 5% overhead. There are algorithms and implementations coming from some of the research that can improve that dramatically. Lucene won't take native code in its. You can't contribute native code to Lucene, but OpenSearch does have native code that comes with it. It uses JNI or JNA to talk to the native code. So you can contribute native implementations of things as long as they exist for most of the CPUs that we target. Just think about broad compatibility over time. And I think a lot can come from reusing elements of an ecosystem that is increasingly native in this engine. So trying to sum this up, it's no longer a question whether OpenSearch can scale to hundreds of terabytes of data. We've shown you clusters that scale to hundreds of terabytes of data just fine. But just fine is really difficult at these sizes. And if we think about the future of OpenSearch that wants to 10x the sizes of data following the trend of the growth over since 2012, the last 10 years, in the next 10 years, we're going to more than 10x the sizes of data, search, and all workloads again. So how do we do that? And we don't think that the current monolith works well for the next 10 years. We can't just keep throwing nodes at the problem or fixing each individual bottleneck. Now, we must do that anyway, because that's where we're going to get incremental gains at every step of the way. But fundamentally, we have to rethink what the software should look like over the next few years. And we think, based on the experience that AWS has, is that the future is increasingly cloud native. Now, that does not mean that OpenSearch needs to run in the cloud. That's not what I'm trying to say. But in cloud native systems, you have different subsystems that exist independently. And you can separate reads, you can separate writes. You can separate search, you can separate indexing. And you can run these individual processes independently, potentially on separate computers, so that one does not interfere with the other. The idea is that I can reason about an OpenSearch cluster in the future with a calculator. And I can say, this is the kind of read workload I have, this is how much data I want to store, and this is how much data I want to write. And I should be able to tell you very easily, without an ML model, how many nodes I will need for something like that. And I should be able to add these nodes easily, and I don't want anything to break, I just want it to work. So we can scale with the data and with the search patterns that we have. So we ask for your help. This is all developed in the open. Come look at the projects that are ongoing, contribute ideas, contribute code. We think we can turn OpenSearch in a more cloud-native-like implementation, the search engine that will work really well for all the existing and future analytics use cases, times 10. Thank you.
Thank you.